problem 7 is similar to problem 6, except that you've made a mistake. You've left some slack in the line. And so instead of having a taut line holding the mass in place, you've got slack, and the amount of slack you have in this instance is 4.52 centimeters. And so as you take off, relative to the aircraft, what's the mass doing? It's going that way. And it's going that way with the same acceleration the aircraft's going the other way. So you've got an acceleration here of 0.429 Gs, which is pretty significant. 0.429 times, right, times 9.8 meters per second squared to get to what your acceleration is. Okay, so we know the acceleration. We know Young's modulus for this strap. And then we're going to take the strap, we've got our thickness and our width. And so just like in problem 6, convert those to meters. You need to do that. We're going to convert the length, um, uh, the slack length to meters as well, to get where our velocity is. We'll get there in a second. But we're going to leave this, or we're going to take that and convert that into millimeters, because at the end of the day, we want millimeters. So what's going to happen? You're going to take off. This load is going to slip backwards until the strap is taut. And at the time the strap gets stretched out all the way, it has some velocity v. And that's why I gave you this equation, because, all right, we know v naught. V naught is 0. We know x naught. X naught is 0. How far does it go when all this is happening? Well, that's the slack right there. X is the slack in the line. That's how far it's going to slip before things change. So in this case, 4.52 centimeters is that X. And so you go through and you figure out how fast is this going when it hits the limit of the strap. And then I gave you a nice little hint here. We're going to use conservation of energy, and we're going to treat the strap like a spring. If you treat it like a spring, make all the writing go away, treat it like a spring, then you're talking about we need a spring constant, YA over L naught. And so you know how to calculate A. You're going to convert the thickness and the width into meters, multiply them together. That gives you your area. You know Young's modulus right here. And you know the nominal length of the line of the strap, which for this calculation for K is YA over L naught, you need to convert it to meters. So instead of 23.15 centimeters, this would be 0.2315 meters. And that gives you your spring constant. Well, now we're going to use, now we know the spring constant, we know the velocity, we figured that out, and we're just going to use conservation of energy. 1/2 mv squared, and so that's our velocity from down there, equals 1/2 kx squared, which is the energy you end up putting. This is the kinetic energy you have. All that kinetic energy is going to get converted to potential energy in the strap as you stretch it out. And what is that x? That x is, in fact, the delta L we're after. That's the change in length we're after. And so you go through, you calculate this, you're going to get delta L, the halves cancel out, and there's going to be what? M over K V squared, M over K V squared, all of that square root. And so that's going to give you your answer in meters, and you're going to need to convert meters to millimeters simply by dividing and multiplying by 1,000. Right? Multiply meters by 1,000, you get 2 millimeters. And that's it for problem 7. And what you should see is um, in this problem, the strap stretches a good bit more than it does in the previous problem in problem 6. Right? In problem 6, where you have it tight, it stretches some, but not a lot. Problem 7, it's got to do the job of pulling the mass along and canceling out all that kinetic energy it got sliding across the floor. And so it's going to stretch more in problem 7. And that's it for problem 7.